Bismillah Rahmanir Rahim. Okay, let's continue from where we stopped in the previous video. And what we discussed in the previous video was the uniqueness theorem that was summarized by saying that the Taylor series of any function f at any point c in a certain interval I is the only power series of this form, right? And that can be possibly represent f on I, but it doesn't say that f is equal to the power series unless we insert some remainder function here. Okay, so and also we tried to understand the existence of the Taylor series, that when or I must say existence of the power series, that when power series is going to be used for the polynomial as a polynomial approximation for any non-polynomial function. The condition was that at once when you keep on increasing the number of terms, then the difference between the original function value and the polynomial function will keep on minimizing. So once if the polynomial is showing such kind of behavior, then only in that case the power series can behave as a polynomial can behave well and can be used for the polynomial approximation of any function f. So we just managed here this function, this equation. You can see this is a non-polynomial function. This was said to be the Taylor series, and this was the remainder function introduced by the Taylor. And we are having several remainder functions here, and but the chief remainder function that is used is named on a French mathematician, Joseph Louis Lagrange, and that function we are going to use while maintaining the proof of the Taylor series in the later on in this video. So you can see here that we are having a relationship between this function f, which is a non-polynomial function, the Taylor function or the Taylor series, and the remainder function. And this relationship is best expressed here in a certain theorem that I would like to maintain over here. It's right over here. So I've just written here already, and you can see here that if f and all of its derivatives, if they exist and if they are well defined in any open interval ab, and ab could be any real number, and we are having a certain number c also including inside this open interval, then for all x values present inside I interval, the function f of x is going to be expressed like this. You can see, so you see the values starting from here up to here is a Taylor series of up to nth terms. So this is t n x, what we say. This t n x is actually this, from starting from here up to here. Okay, and this is your remainder function. All right, and the remainder function that we are going to use chiefly here is the one that is named on a French mathematician, after a French mathematician, Joseph Louis Lagrange, and it is this. The n plus 1th derivative of this function f at the value Zn, and upon n plus 1 factorial into x minus c raised to the power n plus 1. Okay, now what is your Zn? Zn is a value that lies between x and c. Okay, it is something like this. You can write it that I should write here this. It should be like this. Okay, so it is present between this, and c and x, they are all inside, they are resting in an open interval ab that you call I. Okay, so actually it is something like this, a starting, and you're having some c also, and then you're having some Zn. okay? And keep on going. You're having several values of x here, and finally it ends at b on a number line. So that's what is happening, okay? You're having several x here. So between c and between x, you are having your Zn. All right, so that value, that numerical value, we're going to use over here in and you see the remainder function actually explains the magnitude of error that you could find between f of x value and your t and x value. So this is the error is well defined by this remainder function, and this remainder function also helps in finding out or in determining the accuracy of any polynomial approximation, okay? So it helps us in finding out the nature of the error. So on the basis of the nature of the error, we are going to understand how best we could approximate the polynomial value and the function value. That's it. Okay, so now what we do, as far as this is something that explains the Taylor series. So if we just replace our c by 0, like if we are performing the polynomial approximation centered at 0 value, so if we take c 0, then in that case this Taylor series is going to be reduced into a form like this. Let me write down here that your t and x was actually this. Once when we are using some non-zero value c, in that case it is this. And I'm just going to write first few values. I'm not going to restrict it up to n values. So I'm going to express it as an infinite series here, okay? Something like this, and it's constantly going on, okay? So if I just replace c with 0, like if the polynomial approximation is getting understood or it is getting it is extended around c equals to 0, so in that case your series is going to be written like this. It will be expressed like this, and you're having simply x here. So I can write x at this side, okay? Upon 2 factorial plus, and this is said to be your x cube, upon 3 factorial, and so on. It's constantly going. So this is an infinite series at when your polynomial is centered at c equals to 0. So now this form was introduced by another mathematician, Maclaurin, a Scottish mathematician, I must say. His name was Colin Maclaurin, and his period was this 1698 to 1746. It's just an extra thing. So that's it. So this series was introduced by this mathematician, Colin Maclaurin. So that's why the series is also famous as the Maclaurin series, and it was basically derived from the Taylors. And Taylor was an English mathematician. His name was Brook Taylor, and his period starts from 1685 to 1731. That's it. So you see the polynomial approximation, the power series that best explains or that is best used for to approximate any function. That power series is nothing else but the Taylor series, and I must repeat that power series is not exactly equal to any function value. It is simply an approximation, okay? Its value is not exactly equal that of your f of x, and f of x is the non-polynomial function, okay? It can only be it can only become equal once when you insert a remainder function, okay? So you see there are several. I have said, as I've said already, that there are several remainder functions, out of which we are discussing here only the Lagrange, and another one was introduced by the Cauchy, a Swiss mathematician. Another remainder function was introduced by him. So that is also used here for the polynomial approximation, but presently we are not discussing that remainder function. We are just focusing on this that was discussed, that was named after Lagrange. So now we are going to look over to the proof of this Taylor theorem. Okay, so let's try to understand that thing. Okay, here while proving this Taylor theorem, we are going to take the help of the Cauchy's mean value theorem that I have already explained in one of my previous videos. You can see the link in the description box below. So here, first of all, what we are going to do here is that we are going to consider two functions, capital F and capital G, and we are going to define these functions. Okay, so let f of x is equal to, here I just say it's f of b minus f of x minus f dash x b minus x, sorry, it's negative, and we keep on moving till we get the nth, n minus 1th derivative of the function f of x. Finally, we reach to the nth derivative of this function on n factorial into b minus x power n raised to the power n, and this is it. This is your function f of x. Okay, let me focus it here, and this is something that I say equation number 1. All right, in the same way we are going to define g of x as well. So our g of x here is that's it. This is our equation number 2. All right, that's it. Now what we have to do, we are going to we can understand over here that once when we substitute x value b in both these equations 1 and 2, then they will become 0. If you can assume that if you put b at the place of your x, wherever you're having your x, you just put down your b there, then you can see that it become f of b, then this f of b and this f of b will get cancelled, and wherever you're having b minus x, it becomes b minus b, so all these terms will get cancelled. So in this way, your f of b will become 0 entirely. In the same way, if you put b at the place of this x, then b minus b will become 0. This whole thing will become 0. So in this way, g of b will also become 0. Okay, so that's a common sense. So now we are going to differentiate equation number 1. Okay, we are going to differentiate both sides of our equation number 1. Let's see what we are going to have here. Now you can see that this is a constant number because b is a real number. Once when you insert any number at the place of your x, then the whole function will going to give you a constant value. So this is a constant value actually. So whenever you differentiate a constant number, you're always going to get a 0 value. So I'm not going to write here 0 at this place. I'm just going to focus from here. So the negative sign is going to be copied as it is. Let me write 0 also. Nothing is going to be, there's no harm in it. Okay, so and the derivative of your f of x will become f dash x. Okay, and then you move on here. you're going to use the formula of u into v, the derivative of u into v. So just assume that this is your u and you assume this is your v, okay? So it is going to give you what? It's going to give you u derivative of your b minus x will give you minus 1 plus b minus x, and derivative of your f dash x is going to give you f double dash x. Okay. Let's do one more. Let's come over here. So we can see that 1 upon 2 factorial f double dash x upon 2, derivative of this thing will become 2 times b minus x, and on taking the chain rule on b minus x, it gives me minus 1. And I come over here and I'm going to copy b minus x whole square upon 2 factorial as it is, and I'm going to differentiate my u, so it become f triple dash x. Okay, and the same way you just keep on moving, and we just let's come over here, and I should write here minus sign because I'm everywhere I'm having minus sign. So let's come over here. Okay, so at this place I'm going to differentiate this thing first. So it becomes n into b minus x n minus 1, alright, plus, and then this is going to be copied as it is, and I'm going to differentiate this function. So it will be n plus 1 at derivative. And this is going to be n plus 1 at derivative. Okay, that's how we go. Now let us try to organize these terms so that it will help us in simplifying it. So you see, this is going to be what? Minus minus give you plus, it becomes plus dash f, and over here I'm having plus minus minus f double dash x b minus x. Okay, let's move over here. You can see the 2 factorial is 2, so 2 and 2 will get cancelled. Okay, plus minus minus give you plus, so I'm having f double dash x b minus x. Okay, let's move here. Minus plus is minus, f triple dash x. Okay, and you keep on moving till you reach here, okay? So we know that we are having n number of terms. What is exactly the value of n, we do not know, so we are just simply generalizing this thing. So now you can see that once you are having in n factorial, you're having 1 to n values in a product form. So if we just cancel out 1n from here, you're going to have n minus 1 factorial left at this side. Okay, so, and I just forgot to maintain my chain rule of b minus x at this side, so let me write down here. Okay, so minus minus give you plus, and I'm having now this thing, and then minus plus give you minus b minus x power n upon n factorial fn plus 1 n plus 1 at derivative of your x. So you see there's no need to get confused in that. You can see that all these terms are getting cancelled. This and this will get cancelled. So in the same way, this is also going to have going to be cancelled by another positive of its term. So all these terms will get cancelled, and just the last term is going to be left here. So f dash x the derivative of this first function is nothing but this. All right. And if you want to go more deeply, you can make some more terms here, and then it will further authenticate the concept that yes, all these terms are getting cancelled. Okay, so this is something I just left here, f dash x. In the same way, you're going to differentiate this equation number 2. Okay, so once when we differentiate equation number 2 here, let's see what we get. So once when we differentiate equation number 2, 1 upon n plus 1th factorial will be copied as it is, and we are taking the derivative of this thing, n plus 1. So we are going to have n plus 1 upon n plus 1th factorial b minus x n plus 1 minus 1, and then I'm going to apply here the chain rule on b minus x. Alright, so you see how you're going to write your n plus 1th factorial. It is actually this 1 into 2 into 3 up to n into n plus 1. This is it, the product of all these values. So you see, and this was your b minus x power n into minus 1. So this and this will get cancelled. Just 1 upon 1 into 2 into 3 up to n is left, and along with the minus sign, So let me organize this, how it is going to look. The g dash x is minus b minus x raised to the power n upon n factorial. So this is your g dash x. Alright, now f dash x is there, g dash x is there. Now what we have to do, now we are going to take the help of our Cauchy's mean value theorem. That states what? It states this. That's what it says. Extended mean value theorem, that is also called Cauchy's. It says that if you're having two functions which are continuous on a closed interval AB, and also they both of them are differentiable, well defined on an open interval of AB, then no matter what value you select from this open interval, for all the value of x belonging to this open interval, the derivative of this function will be non-zero. Then the Cauchy's value theorem says, and there is going to exist a certain value belonging to this open interval such that f of b minus f of a upon g of b minus g of a is going to be this. Sorry, it's g. It's g, okay? And once it is non-zero, and in that case, this fraction is going to exist, otherwise it becomes undefined. We know that well. And we have studied from the back that f of b and g of b, both of them are 0 here. Okay, so both of them are 0 here. All right, so we are simply having this. This thing is left here. Okay, negative and negative gets cancelled. So f of a is equals to f dash z upon g dash of z into g of a. All right, this is it. So now what we do, we have just obtained g dash x, we have just obtained f dash x. So at the place of our x, we'll put down our z, and now we are going to substitute in this equation. Let us call this equation as equation number 3 here. Okay, let me move this page a bit upwards. Okay, so now it is going to be defined like this. F of a is equal to f dash z. Let me I have to turn my page just to get an idea. This was your f dash z. Just keep this thing in your mind. That's what we have to write down at the back. Okay, now let us write down this as fast as we can. So it is here, f dash z upon n factorial into b minus z raised to the power n. Alright, at the place of your and g dash z, I will write in inverted form because it is in the denominator. It is in the denominator. So instead of writing over here, let me write down the reciprocal. So that makes sense. So it is this. So I will write this in reciprocal form. B minus z, because it is g dash z raised to the power n. Okay. And what is g of a? As we have written in the beginning, the function g was this. So g of a, at the place of our x, I will put down my a, and that's it. That's what I have to write down here. So that's what we have written. So you see n factorial gets cancelled, b minus z power n, b minus z power n is cancelled. Now what we are having, negative negative becomes positive. We are now having only this and this left. Let us write down here, f of a is equals to f of n plus 1 of function z, 1n plus 1 factorial into b minus a raised to the power n plus 1. Okay, so this is your f of a. Alright, so now we are going to use our equation number 1. Alright, so at the place of our x, we are going to put down our a, and let's see what we get. As you can see, that this was the equation number 1 that we wrote in the beginning of the theorem. So this is it. So you see, at the place of my x, I'm going to put down my a. So wherever I'm having my x, I will put down my a there. Okay, so let us write it down. That's it. And now we are going to put down the value of our f of a that we have just obtained, and it is this. Well, that's what the value of our f of a was. So is n plus 1 upon n plus 1 factorial raised to the power z, value z. Just go with the flow. And then we are going to write this whole thing as it is here, like this. And now you can see all these terms except this. We are going to shift all these terms towards the left side. Okay, so once when we move all these terms except this one towards the left side, it is going to look like this. Well, that's what it looks like. Okay, so this is the Taylor series. You can see this is your remainder function, r in x. Okay, and from here to here, this is your Taylor series. So combinedly it is forming the Taylor theorem. So if we just replace your b by x, okay, and you replace your a with your c, and you are having a form that we discussed earlier. And once when you replace your c with your 0, you're going to have your Maclaurin's form. Okay, so that's all for today, and I hope you find this video helpful. If